Hi everyone, welcome to this session. So today we will be solve this interview question. Okay, basically this is a very important circuit for all of us. Okay, and basically this is called a, single stage op-amp. Okay, stage op-amp. For freshers level, what interviewer will ask you, like they will show you this picture and they will ask you if we make this like this. Okay, let's say VA, VV and V out. Okay, they will ask you what is the, if we make this circuit like this block, then uh, please comment what should be the polarity of this VA and V. Like this is op-amp, op-amp, right? So we need to define what is the inverting and non-inverting terminal. Okay, so this is the first question. Then they will ask you what is the DC gain of the circuit, and then they will make a capacitor here like this, and will ask you to draw the Bode plot. Okay, and we know that to draw Bode plot we need poles and zeros and unity gain frequency and DC gain and so on, right? So these are the questions. Okay, and don't be afraid of this this to tail MOSFETs. Okay, basically this makes a normal current source like this. Okay, so if these two are identical, so then the same I current flows through this branch. Okay, like in DC condition. Okay, and we already assumed that the whole circuit is operating well in DC. Okay, like all the MOSFETs are biased at saturation. Okay, so we assume that all MOSFETs are in saturation. Okay, now we have to do the small signal analysis intuitively. Okay, and we know that so first I will find what is the polarities of VA and VB. Okay, so we, like, how to approach this. So we have two sources. Okay, and one thing I will mention you, VA will be like here, this is a differential pair, right? And we have, like, we are forgetting about common mode signals. Okay, we are considering here about the VA and VB are fully differential signal. Okay, so the overall VA, we know that this will be nothing but V bias plus small signal VCM plus VD by 2, and let's say this will be our V bias plus common mode signal VCM and minus VD by 2. Okay, so these are two signals at VA and VB. Okay, so we know, and we have these two are fully differential signal. Okay, so now to find the polarities of this V and VB, what we will do, we will do the superposition. Okay, so first let's take V on VA is active, so this will be ground, right? So now, and there is a, like, this is a constant current source, right? So this will be open circuit. Okay, like in this. Okay, like this. Okay, so now if we increase this potential, so what will be the voltage at this node? So this is a 180-degree phase shift, right? This is a common source of NMOS, so this voltage will decrease. Okay, so we are increasing the VA voltage and this potential is decreasing. Then what is the potential at this node? So this is a short circuit, right? So this potential will also decrease. Now we can find that this is a, like, from here to here, this is a common source of NMOS, right? So this voltage is decreasing, then what is this voltage will be? So this voltage will be increasing, right? So we are finding that making a node increasing, we are eventually getting a increased voltage. So what should be the polarity of this VA? So VA should be plus, right? And we know op-amp output equation is nothing but A times V positive minus V negative. So if we are making increasing, like we are increasing this potential, so the output is also increasing, right? So we have find that the VA will be the positive terminal. Okay, so this will be our positive, and so there is only one left, VB, so this must be negative. Okay, so you can analyze this. Okay, okay, I am doing that. So now here we are increasing VB and here this is ground. Okay, like superposition, right? So if you increase this, what should be the voltage at this node? So this is, we can see that this is a common source of common source of NMOS. So if this voltage is increasing, so this voltage will decrease, right? So we know that this will be negative, this will be negative. So this voltage is increasing, so eventually we are getting V out is decreasing. So this is our negative. So we have find that this is our positive terminal and this is our negative terminal, okay, and this is our output, okay. So this is like a op-amp, this is a single stage op-amp, okay. And we know that the gain is nothing but, what we do, gm is nothing but gm on times r out, okay. Now the question is, what should be the polarity of this gain, plus or minus? This will be plus, okay, because this is the op-amp, right? So the output is always positive here, right? Now and we know that this will be nothing but gm on times rop parallel ron, right? So we know that, but we are going to do intuitively how it comes, okay. And on mistake all freshers like may do, so I will rectify it in this video, okay, like how to approach to find this r out and overall gm, okay. So okay, this will be gain, right? So now so what we are doing, okay, and we are assume that this PMOSes M3 and M4 is identical and M1 and M2 are identical, like they have similar behaviors, okay, like the GM, RDS and so on, muon, COX and everything, okay. Now for small signal picture, what we can do, so this will be our VDD will be short circuit to the ground, okay, and there we have only small signal and we are cancelling this common mode signal, okay. So this will be, let's say, Vd by 2 and this will be our minus Vd by 2, okay. And this source will be open circuit, right? Like we are assuming this is ideal, okay, there is no RDS of this RDS of this M0 is present, okay. Now how to approach this, we have this circuit. Now actually what people do is, so to find the r out first, okay, r out, what we do, we apply a test voltage here, let's say Vx, and we find the current Ix, and then we take the ratio Vx over Ix. But what people do is, like many freshers can do is, like here this is RDS, right? Looking at impedance upward is RDS of P, and looking downward is RDS of N, right? But this is not correct, okay, this is not correct, this is actually wrong, because there is connected something, okay, this M1 will put some effect, but eventually if you solve this, the final result will be same, RDSP parallel RDSN, okay. But this analysis is wrong, like the upper, like looking impedance upper side is RDSP and downward is RDSN, so this comes in parallel, so R out will be this. So this is actually the final expression, but this is not the correct analysis, okay. So I am doing the correct analysis in the like here, okay. So now we have this okay, let me go. So this is our source and this is our AC small signal ground, and here we have NMOS, okay, and small signal is, this is open circuit, okay. Now to find R out, what we do, and for finding R out, this two will be AC ground as well, right? This is our independent sources, so this is M1, this is M2, and we are doing like this, okay. Like I am mentioning it, but I am not going to write KCL and KVLs and so on, okay. So now we can see that there is two paths, so we have to find this current and this current, okay, to find the overall Ix, right? So let's say this is our I2 and this is our ion, okay, like small signal, okay, this is small signal, okay, small signal ion and a small signal I2. So what we can see is this, like, okay, what is the looking in impedance here, this is a diode connected of PMOS, right? So the impedance looking from here is 1 over GM3, and we know that this is a small resistance, and this is actually GM3 is very less than RDS of 3, like RDS of any of this MOSFET, right? Let's say RDS of 1 2 3 4. Okay, we know that. Now in this branch, what this like in like looking downward, what is the picture? Actually this looking like this is effectively this MOSFET and this MOSFET and this resistance, right, with respect to AC ground, right? like like in downward, this downward let's say make a signal. This downward signal will be seeing this MOSFET, and this MOSFET with respect to AC ground. So if we draw the picture, this will be like the, let's say this is the downward, picture. Okay, so this is ground, so this is our, let's say, and we can write this, right, on our GM3. So this is our ground. Okay, now this like for this MOSFET, if we looking from here, so basically this is a NMOS with a source degeneration, right? Now looking up here, what is the impedance? Because this is a finite impedance, right, and very less than the RDS of any MOSFET. So the looking up here is nothing but 1 over GM1, right, because this is M1 and this is M2, right? The source, the looking in impedance from a source of a NMOS is nothing but 1 over GM. So here we have GM1, like M1 MOSFET. So the impedance will be GM1, right? Because this is finite. If this is infinite, then the picture will be different. Okay. So basically this is a small resistance. So the effective impedance will be looking like this. Okay. So basically this become a, so this circuit becomes like this, right? So this is like this. Okay. This is on our GM1. Okay. So we have to look from this, and this is M2 MOSFET. Then what is the looking in impedance from here? So this is, we know that this is nothing but 1 plus GM2 times RO2 into this 1 over GM1 plus RO2. But here in this case we can see that this RO1 equal to the RO2, because these two are similar devices, right? So and approximately we can write that this will be nothing but GM. Achha, okay, so I am writing GM2 as GM1 because these are similar device, right? So GM1 equal to GM2, and we know that GM3 will be is equal to GM4, and R1 will be RO2, like let's say RDS. Okay, let's say RDS1 will be RDS2. Okay, and RDS3 will be equal to RDS4. Okay, so this is the meaning of the identical device. So now we can write this will be nothing but, we can neglect the lower terms, and we will assume the higher term. So this will be nothing but GM1 times RDS1 times 1 over GM1. So actually here in this case, this GM cancels because these two are identical. So we are having only RDS1 or RDSN, whatever we can see. Now I will write in this like conductance format. Okay, so the conductance looking here will be nothing but 1 over RDSN. So the conductance looking downward will be GDSN. Okay, basically the conductance is nothing but the 1 over this, right? So the looking downward conductance will be GDS1. Okay, we have find that. Okay, now we have to see the upward, right? Okay, let me do that again. So okay, let me again do that. Okay, so we have this. Okay, actually I am doing some wrong. Okay, let me do. Okay, so here I have done a mistake, right? Because this term will be effectively this, but there is present RO2, right? So we have to add this. So this will be nothing but RDS1. So we are getting the looking downward impedance is nothing but like let's say this will be nothing but 2 RDSN. Okay, 2 RDSN, because we cannot neglect right now, right? Because this is a, like this is RDS1 and this is also RDS1. So we cannot write like approximately equal to RDS1 because this become 2 RDS1. Okay, so this is the mistake I have made in like in few minutes ago. So this becomes 2 radiation. Then what should be the GDS, like GD, like the conductance, this will be nothing but, let's say, Gn. Okay, so this will be nothing but or let's say G1. Okay, G1 will be nothing but uh, GDS n by 2. Okay, so this is the conductance. So what I would, so this will be nothing but GDS n by 2. Okay, now I will draw the picture again. Okay, this is wrong. Okay, so this will be like this, and this is the round. Now, so this will onward GM3. Now we will look upward. Okay, what is the current going in this way? So we can directly see that there is a present RDS4, right? This is M4, right? Now actually in this branch there is two current. One current is due to the RDS4 and one current due to this current mirror effect. Okay, because whatever the current flowing through this current will be like, this current will flow in this branch as well, right? So this is due to, like, this second current is due to this current mirroring effect. Okay, and this first current is due to this RDS4 effect. Okay, so basically there is two current. What is the current is what is the two current? So this is nothing but, we are doing I2 will be nothing but I1, the current flowing through this branch actually is copying to this branch. So this will be I1 plus Vx by RDS4. So this is the total current, right? So what I am telling is, in this branch there is two current. One current is flowing through this RDS4 to the ground. Okay, and another current is flowing, the current flowing in this path. Okay, so this current will be mirror in this in this branch as well, right? So basically there is two current, and the current is nothing but this current. This is nothing but I1, we have assumed that, and the current this is nothing but, this is Vx, right? So and this is ground, so the current will be nothing but Vx by RDS4. So what is the impedance looking up here? So I will write in like conductance format. Okay, so we know that the conductance looking here was GDS n by 2. So this will be nothing but GDS n by 2 plus this conductance, right? So what is the conductance? If we have RDS4 has resistance, what will be the conductance? This will be nothing but GDS4, and this is nothing but 1 over RDS4. So we have two conductance, right? So this will be nothing but GDS4. Okay, so we have two path having two conductance. Okay, so what will be the overall conductance? So this will be nothing but, we have to do the summation, right? The total conductance. So this will be nothing but, okay, so total conductance. And you can do is in resistance format as well. I am doing in conductance format. Okay, so this will be nothing but, let's say, okay, so the upper was GDSn by 2 plus GDS4 plus this was the upper conductance, and lower conductance was the GDSn by 2. Then what is the overall conductance? So overall conductance will be nothing but, so this will be nothing but GDSn plus GDS4. Okay, so this 4 means this P, right? So we can see that two conductance comes in like in summation format, right? So the resistance, what will be the resistance? So this comes in parallel, right? If we convert this in resistance, so the total resistance, total R out will be nothing but this ROP parallel RON. So we are getting the same thing, but the actually the circuit behaving in this manner. Okay, so we cannot directly say the output impedance looking is nothing but RDSn, and this is nothing but RDSP. So this is actually wrong, but eventually the effective output impedance becomes same, but the analysis is wrong previously. So this is our correct analysis. So now we have find that the total resistance. Okay, now we have to find the overall GM, right? Now to find overall GM, how do we do? Actually this is not coming, so we do like we short circuit the output, like, right, we short circuit the output. Okay, let me do again. So basically this is like this. Okay, so this is not, so we short circuit the output with and find the small signal I out to the ground with respect to this VA and VB, right? So this is our VD, right? Okay, and this is our open circuit. Now what will be the our overall GM? So GM is nothing but I out by basically small signal VA minus VB. Okay, what should be the value? And this is our open circuit. Actually what we can do, what we can see is that uh, actually, okay, so let me do that. So this will be like this. So we can see that the impedance looking here is 1 over GM3, and we know that this is a small resistance and we have a short circuit path. Then what will be the impedance here? So this will be 0, right? So what we do, we do an approximation. So basically these two impedance are almost same, like very small, and we are assuming these two are same. Okay, so we can do the symmetric circuit, right? Right, we can do the symmetric circuit. Okay, so if, okay, let me do, so so I will do in like later case. Let me do the following first. Okay, not coming. Okay, so we know the overall GM is nothing but GM. So from where we come into this conclusion? So basically we can see that if there is a current and we are neglecting or the RDS to find the overall GM, right? So this current is flowing in this path, right? And this current is also flowing in this path. So there is like the total I out will be nothing but I out will be nothing but like, so basically this current, and we, if we apply KCL here, so this current is, let's say this, and this current is outgoing. So so we can make I out is nothing but, so all three are outgoing, right? So this will be plus, let's say IP, and let's say IN. Okay, so I out plus IP plus IN will be 0. Okay, now we have to find the like IP and IN, we like in with respect to this VD, right? The differential voltage. Okay, so if we do that, so this will be nothing but if we neglect, we will get VD. Okay, like this, basically our input was VD by 2 minus VD by 2, right? So the input will be nothing but VD itself. Okay, so so what we can do, so let do that. So basically what is the current flowing through this branch? So this will be nothing but GM times, actually we have to find this. Okay, but we will do the normal cases. So we will do the VD by 2 here, and here minus VD by 2 here. Okay, so basically here what is the current? So we don't know what is the potential at this node, but we can assume, if for symmetricity, we can assume this will be AC ground, right? If we make this symmetric circuit, we know that, right? Because this is a small impedance and this short circuit part having a same small impedance, so we can make this circuit as symmetrical circuit. Okay, so this will be, and if this is symmetrical, so this point will be AC ground, AC small signal ground. Okay, so now we can see that what is the current flowing through this branch. So this will be nothing but GMN times, what is the VG is minus VD by 2 and minus 0. This is 0, right? VS, small signal VS is 0. So the current is nothing but minus GMN times VD by 2. Okay, so this is the our I peak IN current. Okay, and how to be our IP current? So basically there is two current, right? Because one current is through this like what I can say through the like dependent sources, and another current is for this current mirroring effect. Okay, so what is the current? So we will find that. So this will be nothing but IP will be, so this same current will flow through this branch as well, right? So this will be nothing but IN plus what is the GMP, let's say GMP times what is the VG. Okay, okay. So we need to this VG, right? We need to this potential. How would be the this? What would be this potential? This is symmetric. We have taken, so this will be AC ground as well. Okay, right? And they are, if this is AC ground and this is also AC ground, what is the VGS of P? So this will be 0. So there is no dependent sources. Okay, so actually only this current will flow, like the current mirror in, like the current coming from this current mirror will flow this branch. So there is no dependent current source because the small signal VGSP is 0, right? So we have find that, so this is 0, right? So we have find IP equal IN, right? So what would be our I out? So this will be nothing but I out would be 2 of this, right? 2 of this, like if I out will be the minus of IP plus IN, right? So this will be nothing but minus, and basically these two are equal, right? So this will be nothing but 2 times IN, right? And if this is 2 times IN, so what we are getting? So let's say again I out here, minus of 2 into IN. What is the IN? IN is this part, like minus GMN times VD by 2. Okay, minus, this is minus, right? So and this minus cancels, this two cancel, so we are left with I out over VD is nothing but GMN. Yes, so this is the way how we find the GMN intuitively. Okay, so to find overall GM, what we do, we know we have to short circuit the output to the ground, and we have to find the I out. Okay, and our overall GM for the differential pair will be nothing but I out divided by VA minus VB, small signal, right? So and we have to do the small signal analysis, and we have assume on case, because these two impedance is almost like very low. Okay, so we can assume they are in symmetrical behavior. So this point, like the point of symmetry will be AC ground, right? In terms of voltage, so this is ground and this is ground, so our analysis becomes easy, and this makes sense also. Okay, so we are and if we do the current mirroring effect and the normal circuit analysis, you will get the I out, small signal I out over VD will be our GMN or nothing but GM1. Okay, so this is how we can find the overall GM. So we have find that overall GM will be nothing but our GM1, and overall R out will be nothing but ROP parallel RON. Okay, and okay, so and we have find this result intuitively. Okay, not writing KCL and KVLs. I think probably Bejad Radhavi sir makes full calculation on his YouTube channel, but this takes a lot of time. Okay, lot of time. Okay, so you can do in your life once. Okay, for the calculation what Rajavi sir has done. Okay, in his YouTube channel. So okay, now we have to do this thing, right? So this is plus, this is minus, and we have a load capacitor, right? And this is our V out, and we are having this is VD, right? We are finding small signal, and this is our DC gain. So we are finding this is a DC gain. So A is nothing but a GM on times ROP time parallel RON, right? So this is our gain. Okay, now what is the Bode plot of this circuit? So for Bode plot we need poles and zeros. Do you think there is any zero? No, right? Because there is like no two frequency dependent path from input to output. So there is no zero, okay, in this circuit, and you can find the zero is present or not. So like how many capacitor are there, you have to short circuit the capacitor, and then see after short circuiting this that capacitor, the output is zero or not. If the output is zero after short circuiting this capacitor, so due to this capacitor there is no zero. So we can see that if we short circuit this capacitor, so the output is 0 voltage, right? So due to this capacitor there is no zero, okay. But if there is a capacitor, like there must be a pole, okay, because this is a storing element, okay. But what should be the pole? We know that to find the pole, we need to find the effective capacitance due to this node to the ground, and we have to find the effective resistance from this node to ground, okay, AC ground, okay. And we have done that. So if we further redraw this, so this will be nothing but a GM, right? GM of small gm on, and a R out of ROP parallel RON. Okay, so we can write that, right? And there is a capacitor like this CL. So this is our V out. Then what should be and we have to do all the independent sources are inactive. Okay, so what do you think? What will be the pole? Basically, this is the pole. Okay, this segment is contributing output. So the pole will be nothing but. So let's say the overall output conductance is nothing but GO, and this is nothing but R out. Okay, so what should be the pole? So pole location will be nothing but GO by CL. Okay, so basically this is our effective resistance, and this is our effective resistance from this point. Okay, so this is our pole value. Now we have to do the another thing. We have to do now. Okay, so let me draw the Bode plot first. So our Bode plot will be looking like this. So this is our DC gain, this is our A, right? So this is our, let's say, mod of AV. Then we have a pole. So what will be the pole? So this pole location will be this GO by CL. Okay, but we need to another point. What is the point of this? Like this is omega, right? So this is called unity gain frequency. Let's say omega u. What would be the value? We know that the unity gain frequency is a frequency like at that frequency when the gain becomes 1 in linear, right? And gain becomes 0. This is 0 dB, right? And if we make 20 log 1, this will be 0 dB, right? So now we have to find this point, okay, this point. So from this expression we can directly found that. So what will be our expression of this like transfer function? So V out by Vd in S will be nothing but we know that the DC gain, we know the DC gain and some poles and divided by some zeros, right? DC gain into zeros by poles, right? This is the format. So DC gain we have find that. So what is the DC gain? So DC gain is nothing but GM on by, let's say, GO. Okay, let's say GO. GO is the output overall output conduction. So this will be nothing but GM on by GO. This is our DC gain, and there is no zero. Okay, so we are not going to write that. And for pole we can write that 1 plus S by, what is our pole location? Pole location is nothing but GO by CL. So if we make this equal to 1, okay, if we make this equal to 1, we will directly find the what is the unity gain frequency. Okay, so you can do that. Okay, you can do that. So now okay, so you will find that unity gain frequency will be nothing but GM1 by CL, and this makes sense. Okay, this makes sense. You will get this value. Okay, what makes sense is because we can see that this omega u will be further from this pole. Okay, this is pole because this is our GM1 by CL. We know that this transconductance of this Mosfet will be more than this output conductance, right? Because the output impedance is nothing but this, and this is very high, like this is very high value. So in the 1 over this value will be low, right? So if this value is low, so this pole is more close to the origin. Okay, so this is how this makes sense. The unity gain frequency will be at higher frequency. Okay, So if I make some conclusion from this session is that, so we have this structure. Okay, let me do. Okay, we have this structure. Okay, okay, let's say there is a current source. Okay, because this part I am not going to write. Okay, and this is our VDD and this is our V out. Okay, so we have found that, and this is M1, this is M2, VA, VB, and we can convert this like this. Okay, plus minus VA, VB and V out. Okay, and we have a capacitor CL. Okay, and we have a capacitor CL, and furthermore we can convert this like this, plus minus, let's say this is VD, and there is a output conductance and a CL. Okay, so this is basically a practical single stage op amp. Okay, single stage op amp, and we find that Bode plot. This will be like this. So DC gain will be nothing but A will be nothing but DC gain. So this will be nothing but GM1 into ROP parallel RON. This see, this is a single pole system, right? So this omega P1 will be nothing but GO by CL, and GO is nothing but 1 over ROP parallel RON. Okay, and this GM is nothing but GM1. Okay, and this is our GO, and this omega u will be nothing but GM on by CL. Okay, so these are the conclusions from this lecture. Okay, so thank you everyone. If you like our like this session, you can subscribe and please give your valuable feedbacks. Okay, thank you.